So our quantum mechanical model that we just talked about with the S, the P, the D, and even the F subshells, sublevels, all of those models from a mathematical standpoint only work for hydrogen-like atoms, so atoms with a single electron. So how is this useful for us? Because most of our atoms that we work with have many more than one electron. Well, it turns out that we can use the same ideas, and of course the quantitative part of it is slightly different. We have more protons in the nucleus, so that changes the energy of these things. But we end up with the same basic functions and shapes, so we can use those as we progress from a single electron atom like hydrogen or a lithium 2+ ion or a helium ion to more complicated atoms. The key difference when we move on from a hydrogen-like atom is that we have multiple electrons. And the result of those multiple electrons is that it is going to separate the sublevels within a principal energy level. So for any given value of n, we'll find that the L values within that sublevel will vary. All right, so we'll see that in just a moment. But it's not going to be a horribly complicated thing for us to deal with. So here we see the result of that. In the second principal energy level, the S and the P orbitals have separated by a certain amount of energy. All right? And again, this is due to the fact that now you have more electrons in there. And so electrons that are in some orbitals are going to change the energy of those other orbitals. Now you'll notice that they still follow, so that the L values, if we remember that L value corresponds to the sublevel, that in terms of energy, down at the low end, we still have our S, or L equals 0. A little bit higher up, we have our P's, or L equal 1, our D's, or L equals 2, and our F's, or L equals 3. So we see that if we look at the third level here, the 3S, 3P, and 3D, how they successfully get higher in energy. The other thing we want to notice that within a sublevel, so within the 3Ps, those three orbitals are all at the same energy, or they are degenerate. And we see that word here that we talked about in the last session. So any energy levels that are or any orbitals that are at the same energy level are referred to as being degenerate. If we expand on this to go up even further, we go up past the 4S's to the 4P's, 4D's, even into the F's and the 6's. You can see kind of how those energies lay out. One of the things that we're going to need to talk about in class to kind of clarify is, what happens here with this 4s. You see that the 4s orbital is actually lower in energy than the 3d. Well, it turns out that this is more or less from an idealized standpoint, that when we take a single atom and we're adding electrons to it, we're going to use something called the Aufbau principle. We'll talk about this in just a minute, where we're going to put electrons into the lowest energy level first. So it's been shown that the electrons end up going into the 4s orbitals before they go into the 3d orbitals. So in terms of filling electrons into these orbitals or spaces, they're going to go in there first before the 3ds. Now, from a practical standpoint, once we take that atom and we put it into some other environment with other atoms, either in a compound or some other situation, those 4s electrons actually bump up in energy above the 3ds, and it goes back to what we would normally think of. So that's a consequence of putting electrons around a nucleus versus what's actually happening when this thing's reacting. The three principles we're going to use in coming up with the electron configurations for elements are first the Aufbau principle, which tells us that we're going to fill the lowest energy level first. So when we look at the chart here, we're going to start at the bottom with the 1s's. So you can see we've already done hydrogen here, which would have one electron, which would go all the way down in that 1s orbital. And then we're going to follow what's called the Pauli exclusion principle. This is what caused us to come up with the quantum number for the spin. The Pauli exclusion principle says that no two electrons can have the same four quantum numbers. So for instance, if we go ahead to the next element, so we'll go from hydrogen to helium, you'll see that there are two electrons in the 1s orbital. So the configuration would be 1s2. Well, both of those electrons can't have the same four quantum numbers. So one of them would be n equals 1, L equals 0, m sub L equals 0, m sub s plus 1/2. The other electron, still n equals 1, L equals 0 for the s, m sub L equals 0, but m sub s would be minus 1/2. So it would have a spin in the opposite orientation. Okay, continuing on from helium, we go to lithium, 1s2, 2s1, to beryllium, 1s2, 2s2, to boron. Notice now we've gone into 2p's. When we go on to carbon and we add another electron, we've got kind of a choice here. We could put the electron into the same orbital as that first electron in the 2p's in the boron, or we could put it into its own orbital. And of course, we've talked about this already. But electrons are going to tend to repel themselves, so it would more likely go into, or minimizing energy, it's going to go into an orbital by itself before it doubles up. And this is Hund's rule. Right? The fact that we're going to spread out before we double up within any degenerate sublevel. So there's carbon, nitrogen, and it wouldn't be until oxygen where we would see a doubling up of electrons in the 2p orbitals. Moving on from oxygen, fluorine, neon, and so we reach that noble gas, which again is a stable configuration because we've basically filled up the entire second level of electron configurations, the 2s's and the 2p's. As we go through these, the one thing we want to kind of keep in mind is how many valence electrons there are. So recall that valence electrons are the electrons in the highest principal energy level. So in the case of neon, the highest principal energy level is 2, so we would have 8 valence electrons. So we go on to the next one, sodium. Now we've moved up to third energy level. Sodium would have 1 valence electron, that 3s1. At this point, it might be useful also to talk about the condensed electron configuration. So for sodium, the valence electrons are going to end up being the most significant part of these. So we could write sodium as 1s2, 2s2, 2p6, 3s1. However, if we take this part right here, that part right there can be represented by the noble gas neon, and then add the valence shell after that. Right? So these would be two separate ways. Again, the second way using the noble gas would be the condensed electron configuration. Go on to magnesium, 3s1, aluminum, again following Hund's rule, spreading out. We can go through the whole third period of the periodic table. Everything seems to be going all right. Potassium, calcium, scantium. So now we are into the D block of the elements. All right, so here's our D block. You notice that we do have the periodic table listed in the expanded form here. So the transition elements, I'm sorry, not the transition elements, the lanthanide and actinide series are actually included in the table. So we go along, titanium, looks good, vanadium, uh-oh. We get to chromium and something happened there, right? One of the electrons from the 4s actually jumped up into the 3ds. Again, it's all based on energy and stability. Though those energy levels are close enough together that it ends up being more stable having that electron up in its own sublevel, up in the 3ds, rather than being paired up in that 4s level. So as you add more electrons, you know, those energy levels are getting closer and closer together. And so it's minimizing energy by taking one of those electrons in the 4s and putting it up in the 3ds. We go on to the next one from chromium, and we fill that electron back into the 4s's, showing that they are actually, you know, lower in energy in the 3ds. Still at that point, only from a fill-in standpoint. We keep going along, and we see this happen again at copper, where we borrow one of the electrons to, you know, populate the 3ds, and then the other electron from the 4s gets moved up there. Right? And so we can keep on going, you know, going along with these, and up to the 4p's, and et cetera, et cetera. So you can go through, your book gives you a description of all of these things. One thing we can do, you know, just for interest's sake, if we look at lanthanum, we see that lanthanum has this configuration of a 5D, a 6s2, which we would expect being in the 6th period here. But that 5D, you know, normally we might think that that should be over, you know, the element over here would be the D's, right? Again, this is just a minimizing energy idea. If we go on from lanthanum to the next one, notice that we have one in the 5Ds, and then the other electron goes into the 4Fs. Okay? These, you know, kind of, you know, differences aren't things I'm going to expect you to know yourself, but understand that if I showed you this, you know, you would be able to, you know, understand that, you know, we're just dealing from an energy minimization. As we put electrons in, where is the energy minimized? And we can keep going on, and notice it gets even trickier when we get to praseodymium, where, yeah, now we have no electrons in the Ds, and they all go over to the Fs. All right, so you can practice doing these, and of course, you know, writing out the condensed electron configuration is something we want to do for any element on the periodic table. One of the things that helps us with that, and then figuring out how many valence electrons, one of the things that helps us with that is, you know, realizing that the periodic table in general is separated into different blocks. So we have the S block in blue here. We have the P block in red over on the right. We have the D block, or the transition metals, in the yellow, and then the F block, or the lanthanides and actinides, in the grayish color. So we'll do some practice with this. We'll actually even have a race to see who is the best at writing electron configurations.